Welcome back, everyone, to our continued discussion of classification performance metrics. In part 3, we'll talk about ROC curves. Let's begin with a little bit of history. During World War II, radar technology was first being developed to help detect incoming enemy aircraft. However, the technology was so new that the US Army actually wanted to develop a methodology to evaluate the radar operator performance. Since the technology was so new, it was difficult for certain operators to actually tell what was an aircraft versus a false alarm. So they developed the receiver operator characteristic curve. Essentially, whenever an operator was trying to determine whether something was an aircraft or a false alarm, they were essentially trading off true positives for false positives. A true positive would be truly seeing an incoming aircraft on the radar and reporting it as such, and a false positive would be misreading the screen and saying there was an aircraft there when there was not. So to make sure that you would only employ the best operators to read the incoming radar data, the US Army developed this receiver operator characteristic curve. And you can imagine that if we actually mapped out false positive rate versus true positive rate for someone that was randomly guessing, you would actually go a perfect diagonal across this, because you would get just as many true positives as you would false positives if you were just randomly guessing. However, if you were to perform better than a random guess, then your rates should be above this line. Essentially, you're getting lower false positives versus true positives. So let's actually talk about how we construct this line in regards to a logistic regression model. Essentially, the main idea being there's a trade-off between true positives and false positives. And this stems directly from the confusion matrix. Let's begin by trying to understand this in regards to our previous infection test. So we have this test for a virus, and we say there's a 0 if there's a negative test, and a 1 if there's a positive test. Essentially saying class 0 means you don't have the virus, class 1 means we think you do have the virus. And so we take our training data, and we have red points here that are negative as the actual status, and blue points which are positive for the actual status. And we're checking some sort of RNA level. And so off of this training data, what we're going to do is fit a logistic regression model. And then, given some X feature, that is the RNA level, we predict a 0 or 1. So this is obviously a very simple logistic regression with just a single feature. Now the default cutoff point that we chose and talked about earlier was 0.5. So let's imagine that we chose the default 0.5 as our cutoff. That means anything above 0.5 we'll go ahead and classify as a positive infection. Anything below 0.5 we'll classify as negative. So the question arises, how many true positives do we have versus false positives? If we actually count out true positives, false positives, and false negatives and true negatives, we get the following: 3 true positives, 1 false positive, 1 false negative, and 3 true negatives. Let's count these out. Here we can see the 3 blue points that happen to be above the threshold line of 0.5, which means for those 3 X values of RNA, we went ahead and mapped them as positive for being infected with the virus. And we know their actual status happened to be positive. That's essentially our Y known value. So those 3 points we got correct, so they're 3 true positives. Then let's take a look at the true negatives. Here we have 3 red dots that are below the 0.5 line for that X value on the logistic regression curve, and we see that we correctly label them as negative for the virus. Now let's take a look at this point that actually the status was negative, but we classified it as positive. This means we have 1 false positive that is above the cutoff value of 0.5. You'll also notice that we have a false negative, meaning we have 1 point that is below the cutoff value of 0.5, which we reported back as not having the virus, but in reality, they were positive for the virus. But what happens if we actually lower the cutoff? In theory, our cutoff could be anywhere between 0 and 1. It doesn't have to be 0.5. So let's examine a cutoff of 0.4. Here we can clearly begin to see that as we're lowering this cutoff value, we're essentially lowering the threshold of the X feature value needed in order for someone to test positive according to our model, allowing us to have more false positives in order to reduce the false negatives. Now you may be wondering, why even bother adjusting this cutoff point? Why not just have an equal number of false positives and false negatives? Why would we want to increase false positives in order to reduce false negatives? Well, in certain situations, we gladly accept more false positives to reduce those false negatives. Imagine that we're dealing with a dangerous virus, and we really want to make sure that anyone that has that virus is going to be found by our test. We would much rather produce a false positive and later do a more stringent examination of the patient than accidentally release someone thinking they're a false negative. Essentially, someone who's actually infected with the virus, but our model told them they were not. The false negative could be extremely dangerous in this situation. So again, what we can do in order to map out the curve is test a bunch of cutoff values and keep track of the number of true positives versus the number of false positives. Clearly, the number of false positives is going to be changing as we adjust this cutoff value. So we simply chart the number of true versus false positive rates for the various cutoffs, and that begins to build the ROC curve. And by changing the cutoff limit, we can adjust true versus false positives. And recall that a perfect model would have a 0 false positive rate and a 100% true positive rate. So it would kind of look like it's taking up the entire upper left-hand corner, where random guessing is the red line. Realistically though, not everything's always going to be that smooth curve. We're going to get something that for a smaller data set is going to be a little choppier because the false positive rate doesn't really change depending on certain cutoffs. The other thing to note here is you have AUC, which stands for area under the curve. That essentially allows us to compare receiver operator characteristic curves for different models. One model could have an AUC of 0.95 versus another model having an AUC of 0.85. The perfect score possible for area under the curve would be 1. And this allows us to directly compare ROC curves instead of having to test all the cutoffs and compare a confusion matrix for one cutoff versus a confusion matrix for another cutoff. We can quickly see the area under the curves compared to each other. Keep in mind that we can also create a precision versus recall curve, which is a very similar idea. You're just testing out the different cutoffs and then measuring precision versus recall for each of those cutoffs. All right, I'll see you at the next lecture where we actually calculate these and create these plots with Python.